A DC motor relies on the fact that like magnet poles repel and unlike magnetic poles attract each other. A coil of wire with a current running through it generates an electromagnetic field aligned with the center of the coil. By switching the current on or off in a coil, its magnetic field can be switched on or off, or by switching the direction of the current in the coil, the direction of the generated magnetic field can be switched 180 degrees. A simple DC motor typically has a stationary set of magnets in the stator and an armature with a series of 2 or more windings of wire wrapped in insulated stack slots around iron pole pieces, with the ends of the wires terminating on a commutator. The armature includes the mounting bearings that keep it in the center of the motor and the power shaft of the motor and the commutator connections. The winding in the armature continues to loop all the way around the armature and uses either single or parallel conductors, and can circle several times around the stack teeth. The total amount of current sent to the coil size and what it's wrapped around dictate the strength of the electromagnetic field created. The sequence of turning a particular coil on or off dictates what direction the effective electromagnetic fields are pointed. By turning on and off coils in sequence, a rotating magnetic field can be created. These rotating magnetic fields interact with the magnetic fields of the magnets in the stationary part of the motor to create a force on the armature which causes it to rotate. In some DC motor designs, the stator fields use electromagnets to create their magnetic fields, which allow greater control over the motor. At high power levels, DC motors are almost always cooled using forced air. The commutator allows each armature coil to be activated in turn. The current in the coil is typically supplied via 2 brushes that make moving contact with the commutator. Now, some brushless DC motors have electronics that switch the DC current to each coil on and off and have no brushes to wear out or create sparks. Different number of stator and armature fields as well as how they are connected provide different inherent speed-torque regulation characteristics. The speed of a DC motor can be controlled by changing the voltage applied to the armature. The introduction of variable resistance in the armature circuit or field circuit allowed speed control. Modern DC motors are often controlled by power electronic systems which adjust the voltage by chopping the DC current into on and off cycles which have an effective lower voltage. Since the series wound DC motor develops its highest torque at low speed, it is often used in traction applications such as electric locomotives and trams. The DC motor was the mainstay of electric traction drives on both electric and diesel-electric locomotives, streetcars, trams and diesel-electric drilling rigs for many years. The introduction of DC motors and an electrical grid system to run machinery starting in the 1870s started a new second industrial revolution. DC motors can operate directly from rechargeable batteries, providing the motive power for the first electric vehicles and today's hybrid cars and electric cars, as well as driving a host of cordless tools. Today DC motors are still found in applications as small as toys and disk drives, or in large sizes to operate steel rolling mills and paper machines. If external power is applied to a DC motor, it acts as a DC generator, a dynamo. This feature is used to slow down and recharge batteries on hybrid car and electric cars, or to return electricity back to the electric grid used on a streetcar or electric-powered train line when they slow down. This process is called regenerative braking on hybrid and electric cars. In diesel-electric locomotives, they also use their DC motors as generators to slow down but dissipate the energy in resistor stacks. Newer designs are adding large battery packs to recapture some of this energy. Brush. The brushed DC electric motor generates torque directly from DC power supplied to the motor by using internal commutation, stationary magnets, and rotating electrical magnets. Advantages of a brushed DC motor include low initial cost, high reliability, and simple control of motor speed. Disadvantages are high maintenance and low lifespan for high-intensity uses. Maintenance involves regularly replacing the carbon brushes and springs which carry the electric current, as well as cleaning or replacing the commutator. These components are necessary for transferring electrical power from outside the motor to the spinning wire windings of the rotor inside the motor. Brushes consist of conductors. Brushless. Typical brushless DC motors use a rotating permanent magnet in the rotor, and stationary electrical current coil magnets on the motor housing for the stator, but the symmetrical opposite is also possible. A motor controller converts DC to AC. This design is simpler than that of brushed motors because it eliminates the complication of transferring power from outside the motor to the spinning rotor. Advantages of brushless motors include long lifespan, little or no maintenance, and high efficiency. Disadvantages include high initial cost, and more complicated motor speed controllers. Some such brushless motors are sometimes referred to as synchronous motors although they have no external power supply to be synchronized with, as would be the case with normal AC synchronous motors. Uncommutated, other types of DC motors require no commutation. Homopolar motor. A homopolar motor has a magnetic field along the axis of rotation and an electric current that at some point is not parallel to the magnetic field. The name homopolar refers to the absence of polarity change. Homopolar motors necessarily have a single-turn coil, which limits them to very low voltages. This has restricted the practical application of this type of motor. Ball bearing motor. A ball bearing motor is an unusual electric motor that consists of two ball bearing type bearings, with the inner races mounted on a common conductive shaft, and the outer races connected to a high current, low voltage power supply. An alternative construction fits the outer races inside a metal tube, while the inner races are mounted on a shaft with a non-conductive section. This method has the advantage that the tube will act as a flywheel. The direction of rotation is determined by the initial spin which is usually required to get it going. Permanent magnet stators. A PM motor does not have a field winding on the stator frame, instead relying on PMs to provide the magnetic field against which the rotor field interacts to produce torque. Compensating windings in series with the armature may be used on large motors to improve commutation under load. Because this field is fixed, it cannot be adjusted for speed control. PM fields are convenient in miniature motors to eliminate the power consumption of the field winding. Most larger DC motors are of the dynamo type, which have stator windings. Historically, PMs could not be made to retain high flux if they were disassembled. Field windings were more practical to obtain the needed amount of flux. However, large PMs are costly, as well as dangerous and difficult to assemble. This favors wound fields for large machines. To minimize overall weight and size, miniature PM motors may use high-energy magnets made with neodymium or other strategic elements. Most such are neodymium iron-boron alloy. With their higher flux density, electric machines with high-energy PMs are at least competitive with all optimally designed singly fed synchronous and induction electric machines. Miniature motors resemble the structure in the illustration, except that they have at least 3 rotor poles and their outer housing is a steel tube that magnetically links the exteriors of the curved field magnets. Wound stators. There are 3 types of electrical connections between the stator and rotor possible for DC electric motors: series, shunt, parallel and compound, and each has unique speed-torque characteristics appropriate for different loading torque profile signatures. Series connection. A series DC motor connects the armature and field windings in series with a common DC power source. The motor speed varies as a nonlinear function of load torque and armature current. Current is common to both the stator and rotor, yielding current squared behavior. A series motor has very high starting torque and is commonly used for starting high inertia loads, such as trains, elevators or hoists. This speed-torque characteristic is useful in applications such as dragline excavators, where the digging tool moves rapidly when unloaded but slowly when carrying a heavy load. With no mechanical load on the series motor, the current is low, the counter EMF produced by the field winding is weak, and so the armature must turn faster to produce sufficient counter EMF to balance the supply voltage. The motor can be damaged by overspeed. This is called a runaway condition. Series motors called universal motors can be used on alternating current. Since the armature voltage and the field direction reverse at the same time, torque continues to be produced in the same direction. Since the speed is not related to the line frequency, Universal motors can develop higher than synchronous speeds, making them lighter than induction motors of the same rated mechanical output. This is a valuable characteristic for handheld power tools. Universal motors for commercial power frequency are usually small, not more than about 1 kilowatt output. However, much larger universal motors were used for electric locomotives, fed by special low-frequency traction power networks to avoid problems with commutation under heavy and varying loads. Shunt connection. A shunt DC motor connects the armature and field windings in parallel or shunt with a common DC power source. This type of motor has good speed regulation even as the load varies, but does not have the starting torque of a series DC motor. It is typically used for industrial, adjustable speed applications, such as machine tools, winding-unwinding machines and tensioners. Compound connection. A compound DC motor connects the armature and fields windings in a shunt and a series combination to give it characteristics of both a shunt and a series DC motor. This motor is used when both a high starting torque and good speed regulation is needed. The motor can be connected in two arrangements, cumulatively or differentially. Cumulative compound motors connect the series field to aid the shunt field, which provides higher starting torque but less speed regulation. Differential compound DC motors have good speed regulation and are typically operated at constant speed. See also, Ward-Leonard control, torque and speed of a DC motor, external links, DC motor, interactive Java tutorial National High Magnetic Field Laboratory, make a working model of DC motor at sci-toys.com, how to select a DC motor at Micromo, DC motor model and Simulink at File Exchange, MATLAB Central, references, Herman, Stephen. Industrial Motor Control 6th ed. Delmer, Cengage Learning, 2010. Page 251. Ohio Electric Motors. DC series motors, high starting torque but no load operation ill-advised. Ohio Electric Motors, 2011. Archived July 20, 2011 at website, Lawton M.A. and Warren D.F., editors. Electrical Engineers Reference Book. 16th ed. Nunes, 2003. Page 19-4. William H. Yedon, Alan W. Yedon. Handbook of Small Electric Motors. McGraw-Hill Professional, 2001. Page 4-134.